All right, guys, let's take a look at topic 2.5. I know that we've started this in class, so I'll just go over what we've done and then I'll continue on, hoping to explain a little bit more in detail. I also added another page into the OneNote so that you guys can practice drawing some Lewis diagrams, putting the electron pairs in the right spots or creating the right bonds. This is going to be the foundation to do the Vesper model, which I'm going to have you guys kind of look at on your own on the side. But this is going to be the first piece of this. So don't forget the Lewis dot structure. Like, we know this from the past. We talked about this before. The different ways to do the dot structures. You can put two at the top and go all the way around. You could start on the right side like I've done before. You can also spread the electrons out in order to make the bonds, right? So electrons are negative. They're going to want to create these kind of electronegative areas, right? Don't forget that certain atoms are going to pull more intensely on the electrons based on their electronegativity. And we're going to kind of fall back on a lot of these ideas as we do this. So we talked about, simple diagrams to complex diagrams, different ways to create diagrams. But what we really need to keep in mind is that Lewis structures here are representing covalent bonds, right? If we want to have an ionic structure, what are we going to need to do? We're going to have to go and create two ions and put them together with those parentheses, those brackets, and the charges on the outside of them. So valence electrons, we can put them as dots between two elements, or we can go and draw them as pairs in between these elements as well. Now, as lines in between the pairs as well. So a dot structure could also be represented by a line, okay? Now, if we have a pair of valence electrons, they're going to be called a lone pair if they're all alone, or they're a bonded pair if they're part of a bond. But these are going to help determine later the molecular shape, which we're going to refer to as the Vesper model. Okay, so the valence shell electron pair repulsion model is just kind of like, hey, what does this thing look like in 3 dimensions? Because here we're going to get an idea of what the shape looks like if we flattened it, crushed it, like drove over it, spread it out, and what does it look like? But we actually want to know what it looks like in 3D later. So we talked about steps. Let's count up the electrons. Let's put the least electronegative in the middle, usually the first element in the compound, or sometimes it's the center one. We don't want to put hydrogen there. We want to put the element that can make the most bonds. So something like, something that's missing as many bonds as possible, like a carbon or a nitrogen or something like that, phosphorus, something in the middle. Count up all the electrons, place a bond in between, see how many electrons you have left. And then we have to try and make some octets, okay? So I know I could go through these, but it's easier to show it than to talk about it, right? So we did a few. We counted up the electrons. I hope you guys remember how to count up the electrons, right? We're going to have to, count all of the electrons that exist in their valence shells. So that's how we got 6. We said, okay, well, how many do we have here? We have phosphorus, which has 5. We want to add, we have 3 chlorine atoms, which have 7 each, okay, for a total of 21. So we have 26 electrons here. Now, we took 3 bonds, okay, we made these bonds that are here, and that bond represents a pair of electrons, don't forget. So we had 2, 4, 6. So we have 20 more electrons to place. Okay, so we take the total number minus the bonded number, and then we know how much is left to place here. Maybe I'll just zoom in on this. Okay. So that's how I came around and we said, oh yeah, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then we're all good. So now I just want to make sure, do I have octets? Okay, the chlorines have 8. The phosphorus now has 8. We're good to go. Okay, so we did those. C and O, same type of idea. We have 6 for each oxygen and another 4 For carbon, so we have 12 plus 4, 16. Originally, with the blue bonds, I had put 2 electrons each there. And then the problem was that carbon was missing some of its octet and oxygen was full. So we pulled a pair of electrons away from oxygen and turned it into a bond. Don't forget, that still counts as 2 electrons for oxygen. It's just that it also now counts as 2 electrons for carbon. So hey, we've got 8 for each. We're pretty happy. Okay. So that explains all that. So then we came into some more complicated molecules. Again, we had some bonds to fold in. We talked about the nitrate atom and the cyanide atom. Now, the nitrate atom, we had a little bit more of a lengthy discussion on, but like why NO3? Why not NO with another O or another 2 O's next to it? Well, nitrogen is the least electronegative, so we want to put it in the middle, right? So you can also see, this is going to come up in 2.6, is that we end up creating what's called a resonance structure. Like you could say, why did it choose to go with that oxygen? Or, like, hey, Benny, why not put it with the other one? Why not put it with, the first oxygen on the left or the bottom oxygen? And well, the fact is that you can. So we're going to see how that works after. This actually makes a very, very stable element when it goes around. But there's something about this nitrate that's different, right? And that's that we put around it a bracket, because don't forget, a polyatomic ion is actually a covalent molecule with a charge. So we had 1 extra electron, and that 1 extra electron, that negative charge, that's over here. We added that into our calculations when we said +1, right? A cyanide being another one. We had carbon had 4, nitrogen had 5, and we can go from there and say, okay, well, if carbon has 4, nitrogen has 5, we have 9 total. My apologies, I was interrupted and I had to take back up the recording here, but we were talking about the cyanide ion, right? And we have a total of 9 electrons in this cyanide ion, right? That are from the valence shell. So 5 from nitrogen and 4 from carbon. So we have a total of 9, but we also have this -1 charge up here, the negative charge, meaning that we have an extra electron on that. So we have a total of the 10 electrons. Okay. Now, if I started, I'm just going to go down here. I'm just if I started and I said, oh, I'm going to put just 1 bond to start. And I'm going to take the 2 electrons off. I have 8 more electrons to place. Like, where the heck am I going to place these? Like 1, 2, I don't know, 3, 4, 5, 6, maybe 7, 8. I put them around nitrogen because it's more electronegative than carbon, but really, we're not satisfying the octet rule for carbon. All we have done is satisfy the octet rule for nitrogen. So what we'll do is we'll steal a pair from above. Let's take a pair off and let's turn it into a bond. Let's take another pair and turn it into another bond, so that we have 6 electrons in that electron dense area in the middle. And then carbon has a 7th and an 8th, and 6. And then nitrogen has a 7th and an 8th. And everybody's kind of happy that way. And then, of course, we put the brackets around it, and we put a -1. There really is no other way to draw that particular structure. Okay, so those are some practice for just your basic Lewis dot structure. So if I come here and I said, okay, well, is that always true? And you're like, oh, great, thanks for telling me the rules. And now you're telling me there's some exceptions. Well, there are a few. There's one like boron. If you look on the table, so boron is one they like to talk about, like we like to talk about. Okay, boron, so that's B. And when we look at B, you're going to see, like, find it on the periodic table. And let's take a look at what we've got for boron, right? You'll see some examples when we get down to the BF3. The other one would be that sometimes you have an expanded octet, it's called. So what the heck is an expanded octet? Well, when you get into the 3rd period that you actually have 3s, 3p, and 3d, even though we don't use them. but actively, or what we think of as being actively. But when we go to bonding, what can happen is some electrons can jump into other positions because it's beneficial. It's like, hey, if I have a roommate, if we split up and we each take our own apartment, we can take on another set of roommates, and those roommates are our electrons. So you're going to see this happening quite commonly with phosphorus, with sulfur. Another one that I'm going to write in here that I didn't mention in the notes here, but you're going to see examples with xenon. I've seen that one quite often. Okay, so we also have hydrogen. Okay, we have hydrogen, which can only have two. So it's not an octet. We could say hydrogen, yeah, it's a duet, but I think we're cool with that. Also, if we have multiple carbons in an atom, they also bond together because they make carbon chains, right? And that's kind of the basis that we have for hydrocarbons. So you have hydrocarbons and they're going to make chains like this. And then basically we're going to call it ramified, but we could add things around these carbons. If those were all hydrogens, for example, in the one I just drew, that would be pentane. I mean, it's 5 carbons, right? So penta and then A, and they got some single bonds. If we took some hydrogens away, we could have double bonds or triple bonds. That's when you get into organics. We'll probably see some molecules, and when they show up, we'll talk about them. But for the most part, let's worry about the main ones. So hydrogen, I mean, this is a no-brainer because they each have 1 electron, so we have a total of 2. And if we put the bond in there, 2 minus 2 equals 0. And we're like, yeah, but there's not 8, right? It only needs to have 2. Methane, see here, here's another example with hydrogens, right? So we have 4, 5, 6, 7, 8 electrons total. So let's put, bonds around the carbons to hydrogens. Hey, we've taken up all 8 of them. A carbon has 8, hydrogen has 2. That's the exception. I mean, we know that. And we've done ammonia before, but we have N, H. No, so this makes ammonia, but nitrogen, it does need to have its full octet because it's still higher up in the period. It doesn't, in the periodic table, it doesn't have extra space. It doesn't have any D's to kind of expand to. We don't need them here. We have 5 plus 3, we have 8 electrons. We've used 6 of them. We need 2 more to place around. You place them around the central atom, and now everybody's already happy, okay? Now, what's going to happen if I draw boron trifluoride? Well, let's just see what happens here. Let's put a B in the middle. And then let's just go F, F, F. I could draw them a straight line too. I just was giving myself some more room. Okay, so how many electrons do we have if we look at boron trifluoride? Well, boron has 3 electrons. Fluorides have 7. So we have 3 times 7. So that gives us 24 electrons to place, okay? So let's see what we do. Well, let's look around fluorines. Let's put our around most electronegative. Okay. So I have, first of all, sorry, I should take away from the bonds. 6 minus 6. So we have 18 left, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we're like, hey, there we go. We've got 2. We only have 6 electrons here. But fluorine is super electronegative. It wants electrons. Should I steal electrons to make a double bond? And what happens here is we just say that B is happy with 6. I mean, it's not ecstatic, but it's happy. Like, why not pull some electrons down from the fluorine and make a 1 bond? Well, the answer to that is who the hell knows? It just is something that's observed, okay? So it's just kind of one of those ones we just got to know. Now, boron mononitride, that means 1 nitrogen with bor, as you can see, Bn. What do we have? We have bor has 3 electrons. Nitrogen has 5 electrons. So we end up with 8 electrons, right? So if I just put a B and an N, and you're going to notice it's like, okay, well, I'm going to put a bond here. So let's take away 2 electrons. So I have 6 left. where should I put these 6 electrons, right? Like 1, 2, 3, 4, 5, 6. Would they all go to nitrogen, or, should we pull some bonds in? Can we pull enough bonds in? Well, let's pull 2 of them in. We can't have quadruple bonds. The most you can have is a triple. So single, double, or triple bond. And you're going to say, okay, well, nitrogen is happy. Boron has 6 of its possible 8. It's about as good as it gets. Again, 6 electrons only when it's done. Now, I would love to say, hey, this is the reason why, and it's really straightforward and it makes a lot of sense. But like a lot of other things here, it just is. And sorry, we just kind of got to know it. So that's boron. Just boron is one of these ones that can have this issue. Noble gases, some larger elements, they will actually have more than their full complement of octets. That you're going to draw them kind of off. It's weird. You draw them kind of off to the side and say, hey, what's going on here? Well, xenon, krypton, they're really big atoms. We know they're really big. They're full, but they're also on the right side. So relative to their family, they're small, but they're down the periodic table. Like the krypton's in the 4th period, xenon's in the 5th. So you got a lot of shells, a lot of overlapping going on. So guess what? We can kind of squeeze a few extra people in if we have to. We're going to sneak them into the theater, okay? So if I'm going to do this, I'm going to put xenon, and I'm going to put fluorine around it. Fluorine, 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 fluorine. And I'm going to say, well, what does xenon have? Xenon has 8, right, electrons around it usually. Fluorine, we have 4 times 7 for a total of 28. And that's giving me 36 electrons that I need to place. Well, I've placed 8 of them, okay? So that is leaving me, what, 28 electrons left to place. Okay, let's try and place those 28 electrons. 1, 2, 3, 4, whoops, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My bad. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All the octets are full. Okay, we're still missing 4 electrons. That only takes us to 24. So what we'll do is just go 25, 26, 27, 28. Why? Well, xenon's just going to, plug some electrons into its d or its f orbitals because there's a little of that overlapping room. And we're just going to say that's where they are. Again, is it normal even for a noble gas to react? You might have said, hey, Vinny, you told me noble gases don't react. And for the most part, that's true. We can kind of force this molecule. It's definitely not a natural molecule. Okay. KRCl3, Cl2. Let's see what's going on here. KRCl, Cl. Okay. And we have 8 plus 2 times 7 is what? We have 15, right? 14 plus 8 is, I don't know where I got 15 from. 2 times 7, 14. 14 plus 8 is 22 electrons to place. I already have 4 electrons placed, right? So I have another 18 electrons to place here. So what do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We need another 2, 17, 18. Just kind of squeeze them in there. Again, it's like these exceptions. You're like, oh yeah, this all works. Oh, nah, crap. Here's a couple that we have to be careful for. C2H3Cl. So now we're getting into some other examples. Give it a try, pause the video, and then I'll pop it back up after you've tried, and we'll see where we're going. Well, if you got it, probably took a little figuring. I mean, these molecules that are organic like this, like when they have bases of carbons, they're not super easy to figure out all the time. But you have 2 carbons in the middle. I put the carbons in. I had 18 electrons to account for, so I put my bonds around one single bonded to the hydrogen, to the carbon, to the chlorine. I put the hydrogens on 2 separate carbons, you would have seen that if I had it all on the first carbon, I wouldn't have been able to do anything with the second. And then I put my electrons in, and I put them around chlorine, the most electronegative. And then I had I couldn't have formed a double bond with chlorine anyway. So I put my electrons around chlorine, and then I had 2 extra electrons. You can imagine I had like 2 extra electrons here. Well, they just peeled in to form a double bond. Okay, so maybe not easy as you see more and more of them, and you see the answers. You start to go, I'm going to recognize some things that happen in these molecules, but that's what we would have. CH2. Again, here's a whole bunch to try. So give them a try, and then I'm going to come back and you guys can unpause the video. So I'm going to pause it, try it, and then I'll come back. Well, I hope that you paused it and that you tried it. And these are the different structures. Notice that I have an ion for B, so I put it in the brackets. For D and E, they were exceptions in the sense that they had expanded octets for sulfur. And boron is one of those elements that can actually be okay with only 6 electrons. Why? Because. Okay, sulfur, why? Because you're in the 3rd period, and it often happens with sulfur and phosphorus, we can expand into like that hidden D block that we haven't tapped into yet. So there we go. Hopefully that's what you got. Now, practice. There's some practice ones to do here. What I'm going to do is I'll pause it, and I'll do the practice, and then I will play it, and you can just give it a try. Okay, and so stop, give it a try, and then check your answers after. There we go. For that one, I had to draw a pair of electrons down from the oxygen to the carbon in order to make a double bond there. That's a very common, it's called a carboxylic acid, that ending. Double bond to one oxygen, then an O and an H onto the other one. That just happens to be the one that I would pull it from. Because I needed to complete the octet for carbon, and I had a few choices, okay? So next page, what I'll just show you here is that you have a few different names, like maybe you want to take a look at like methanol, ethanol, like those type of things. Well, I have that other formula, CH4O. I mean, that might be its empirical formula, but the CH3OH is going to help us because that's going to give us a little bit of an idea how to lay out the compounds, okay? So that's what you want to use. In organic molecules, lots of carbon, hydrogen, oxygen. That's often how it's written. So I'll just do these. I'll start with propane, and I'll do them all, and then we'll show you the answers. Voila, the first one. Hey, everything's cool. We got all the electrons accounted for. It's an alkane. It's got single bonds. Methanol, took away some hydrogen, added an alcohol group. This alcohol group then goes on to the end. That's at OH. And I had 2 electrons. Of course, I placed them on the oxygen because that's the one where the octet was missing. Good. And the next one's very similar. You're going to find that as you get going in alcohols, they're just going to keep going up like this. Added another methyl group in there. Of all of our electrons accounted for. Note that the structure C2H5OH kind of gave us an idea of how to lay it out. C, 2 carbons, an oxygen, then a hydrogen. Don't forget, carbons are always bonded together in these molecules with several carbons in them. There we have ammonia. We had 9 electrons, but it was a +1, so we only had 8. There's the 4 bonds taking up the 8 electrons. Okay. So pause, next one. Hey, there we go. Looked complicated, but we've got 2 oxygens in the middle, hydrogens on the outside. Hydrogens are happy with 2 electrons. We placed the other electrons around the oxygens. There were 8 left, and hey, we've satisfied the octet. Next. Looks like this, but what do we notice? Carbon's missing its octet, so let's steal from one of these oxygens here. We'll have a double bond, so it's going to go like that. Now that's going to cause a resonance, meaning why was it that oxygen? Hey, Benny, why not take it from the one on the left and the one on the bottom? There is no reason why. So we can actually draw it 3 different ways. and we'll say that it's going to resonate, meaning that that bond actually just keeps moving around and makes it crazy stable. That's why the carbonate ion is so popular. Okay, there we go. Nitrous acid, HNO2, two nitrogen oxygens bonds. Okay, these bonds have different lengths. Think double versus single, so that's telling us something that they have different lengths. Okay. The hydrogen atom is bonded to one of the oxygen atoms. Draw the Lewis diagram. Okay, so we're saying let's go put this nitrogen in the middle. Okay, let's do that. Okay, nitrogen in the middle. And now it said it's bonded to one of the oxygen. It's bonded to another oxygen. And then one of the oxygens has a hydrogen, whichever side you want to put that on. Hydrogen is bonded to one of the oxygen atoms. Okay, so now it's also telling you that it has two different lengths. It's not splitting the difference, so it's not sharing bonds, not resonating here. It's saying it's got two different lengths. One has to be shorter. So we're probably going to put a double bond in here, right? And now we've got H and O2. Is that our structure? Do we have all of our electrons met? Let's just double check here. We got to still place them around, right? So we had 6 times 2. We had 12 plus 5. 12 plus 5 is 17. And 1 for the hydrogen was 18. We had 18 electrons. We've now used 1, 2, 3, 4. 4 times 2 is 8. So we've used 8 electrons up through 4 bonds. We have 10 electrons left to place. So let's see where we should go. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's good. Oxygen's good on the other side. Nitrogen's still missing 2. So let's go like that. Right? And that's our structure for nitrous acid. And now there was a key in there saying that they have 2 different, think double bond versus single bond. That kind of helped us out. Okay. Draw the Lewis structure of C2Cl4. So C, now each of these chlorines is probably going to have to, whoops, I shouldn't do it like that. Okay. So I'm probably going to put 2 chlorines on each one. Why not? And we see that we're missing 2 electrons here and 2 electrons here. So we might not have enough. I might have to form some double bonds. Let's just check and see. We have 7 times 4 is 28 electrons from the chlorines. And we have 2 times 4. We have 8. So we have a total of 36. Now we've already used 5. So we've used 10 electrons. So we've got 26 electrons left to place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And we need to have 25 and 26. So where are these other 2 electrons? Would they be on one of these? Well, why not go like this? And let's just put them into the bond in the middle. Because we have to, how can I add 2 electrons? That would make both of those carbons happy. Crap. If I had a double bond there. And there we go. Some good questions. On to the next will be topics, will be the formal charge and resonance. So I'm going to stop that.